Okay, one big deal is that if you have an isothermal, put the R in there and mess it all up so nobody can tell I made a mistake. If you have an isothermal, then you got to put heat Q into the system on that isothermal to heat it up. Okay? And you can figure that out fairly easily because you know the specific heat of a gas, right? Okay? In this case, you don't need the specific heat so much as you just, well, yeah, you do. And you can work that out. Again, monatomic and diatomic. Three-halves R monatomic constant pressure. And it's not constant pressure, it's constant volume. And at constant pressure, you just add R, but I'll write it as 2/2 R, so it's easy to write, add to 3/2 or 5/2, right? And gamma, okay, this is CP, constant CV, constant volume, and this would be CP if you add the 2/2 R. And gamma, what I'm trying to write is CP over CV. Okay? So it's easy to, really pretty easy to understand that. And we tried to develop that idea if you did all the work. Okay? So anyhow, you got isothermal, you got heat going in, right? Now if the isothermal is going this way, you got heat going out. You got to take heat out, right? Okay? Now in an adiabatic, there's no heat transfer. Okay? Okay, so, and we've done this before, but not quite as much detail, but we're kind of reviewing. And this is a great big deal. This is almost an equivalent statement of the second law of thermodynamics, which is one of the 7 or 8 big laws that govern the universe. Okay? And it's one of the most important of all. I guess they're all essential, so it's hard to say what's more important. But, okay, so if we have a process that looks like this. Okay, can you tell which ones are adiabatic and which ones are isothermal? Okay, where do we have heat going in and where do we have heat going out? First place, what direction you want to go around this cycle?
Clockwise.
Yeah, I want to go clockwise because that way the total area enclosed in this thing is positive. Okay? So you have heat going in. And you have heat going out. And drawing it kind of badly now. But you got this thing on a P versus V diagram. Okay?
Have you voted for SGA yet?
Going in this direction.
My name's Adrian Ollinger.
Okay.
I'm running for president.
Okay.
I've been here for 3 years.
All right.
I'm vice president for 2.
Okay. All right. I will do this. Thank you.
Total work is the area enclosed. In other words, the work you do along this path is the area under this thing, right? The work you do along this path is the area under this thing. Now, if you're going backwards, it's the negative of the area under this part of the curve and the negative of the area under this part of the curve, which you should understand completely since you've had a good calculus course, okay? But if you don't, stop and think about it. It's a biggie, okay? And it's just fundamental calculus. You integrate in the opposite direction, you get the opposite answer, okay? Then your delta V's would be negative if you were going in that direction. Your pressure's positive, so this tells you you get negatives, right? Okay? Okay, so total work is the area enclosed. So, you put in heat Q in. I won't even use a W, I'll just say work done is W total, okay? Efficiency is Q in over W total. Now, where is the temperature of this system greatest?
Where the pressure is the least, or no, where the volume is the
Well,
least,
volume has something to do with it,
pressure
right?
is the greatest.
Okay, well, let's just compare this point with this point. How's the temperature here relate to the temperature here? Well, this is isothermal, so it's the same, right?
Yeah.
Now you're expanding, okay? So you're here, okay? And this is isothermal, okay? So your maximum temperature and that's T hot, H for hot, okay? Now what do you think this one is? T what?
T cold.
Yeah, TC. For this system, and if I gave you enough detail, we'd do some of the integrals and stuff like that, I could ask you to prove it. I expect you to get at least part way. Yeah, again, if you'd have done everything I asked you to do, which is probably humanly impossible, you wouldn't need any hints. But QN over work total, right? Turns out that is and this is the maximum possible Carnot efficiency. This is the Carnot cycle. Okay? Got a 5-year-old grandson, just got his first big boy bike, and he probably thinks a Carnot cycle is something he can ride. Okay? Carnot efficiency, right? And it's greater than any other efficiency possible between these temperatures. Okay? So for example, if I take that bottle with the tube and do the experiment we never had a chance to do, we did a lot of others, okay? And we didn't do it because, again, not everything that I needed you to do before we could sensibly do it got done. But we have water, freezing water, let's say, and boiling water. They wouldn't want to use boiling water with a plastic container, but assume it's some kind of a container, thin metal container. that still holds constant volume, right? Strong enough to withstand the pressure. And you put water in the thing and you put a tube out the top, right? And then you heat it up to a certain point, letting water rise in the tube because the gas is going to expand against the water in the bottom, which will come up through the tube, and you're familiar with that, okay? So you're basically expanding a piston. But you're not expanding it much because the tube is thin. The tube is thin, okay? Right? So it's essentially a constant volume expansion, or constant volume increase in pressure. What's that look like in a PV diagram? Constant volume. If volume is constant, it's a vertical line. Okay? Then the water gets to the top of the tube and starts flowing out. Now the water's not rising any higher in the tube. You don't have any more pressure. We assume the water flows out slowly so that the pressure loss in the tube is insignificant. Okay? So the pressure stays constant. What's that look like in a diagram? Looks like a horizontal line because P is constant, right? So you got a vertical and then a horizontal, as in over here, but okay? Then maybe you bring it back to the original pressure by allowing the water in the tube to gradually lower. And you do this slowly so that the temperature remains constant. Okay? And then maybe you do something else to bring it back to its original state. So you get a cycle that looks like this. Well, the integrations are easy. Integration here and here is just multiply pressure times the change in volume. Here multiply the pressure times the change in volume. Change in volume would be negative. And this might be an adiabatic or an isothermal. And now you've got a cycle, and you can figure out the efficiency of that cycle very easily. And I might well ask that. Okay? I'd give you sufficient hints, but something that you should be able to do. You should know that efficiency is the amount of heat you got in divided by the total work. And you should also know that the energy conservation I'm going to write it this way. It's usually written the other way, but you put a certain amount of energy in, you take a certain amount of energy out, and you get some work. If all the forces are conservative, that's it. So what you put in is what you get out. And this is generally, this has to be less than this. So the efficiency has to be less than 0. Okay? Worth thinking about.